let's continue on the review for the chapter or the second test. First thing we're going to talk about with magnitudes about vectors is finding their magnitudes. So if I want to find the magnitude of A, I would take the square root of 3 squared plus 5 squared, which gives me 25 and 9 is the square root of 34. And so that would be the magnitude of A. Remember, the magnitude is basically the length of the vector, and that's why we're using Pythagorean theorem. All right, when we can add components, so if I want to do A plus B, I would take the x value from both of those and add them together, and I would do the same with the y values. And so there's the vector A plus B. Now, component form is what we're using. That's the type. We also have, if I wanted to do a motion of x minus 1 and y minus 2, that is not component form. Component form is where you're using the x, using the vector notation. And if we were going to use component form for most of the stuff that we do. Now, unit vectors is a vector in the same direction as the original one, but it is 1 unit long. So what we need to do is we need to take our vector. I'm going to do unit vector for A. We know that our A vector is 3, 5, and we divide that by its magnitude, which is the square root of 34. And so I get 3 root 34 over 34, comma, 5 root 34 over 34. And so there is a vector that is 1 unit long, and if you put that into the Pythagorean theorem, you would get that it turns out to be 1. And so it's a unit vector. We also have a ij form, and a vector, a unit of 1 for I would be a vector of 1, 0, and j means 0, 1. So there's a couple things that our book calls unit vectors, and this is a vector that is 1 unit long, and this is a vector in the ij format. Dot products and angles between vectors. If I have a couple here and I want to do the dot product, I would take 1 times negative 6 plus negative 3 times 2, and I get a negative 12 divided by the, well, I'm going to call this one u and I'll call this one divided by the square root of 10 times the square root of 36, we'll call it 40 for the fun of it. And then I'm going to do the inverse cosine of that. So inverse cosine of negative 12 divided by the square root of 400 for easy of typing it in. And I get 126.9 degrees. Now, what this formula does is find the angle between the two vectors. So let's take a look at these two vectors and see what we can draw what that's going to look like. 1, 2, 3, 4, 5, 6, 2. And what we have is the angle between these two is 126.9 degrees. And so that's what that is doing. Parametric equations adds a third variable. We show the directions when we graph parametric equations. Let's say I end up with something like that. We put these arrows in there to indicate which direction you're being graphed. know how to eliminate the parameter and how to do ellipses. So let's say I have this being my first thing I want to do is I want to graph it, so I'm going to have a t variable, an x variable, a y variable, and since my t starts at 0, I don't know if I want to go that far. I might just make, just for my ease, I'm going to change that to a 4. So when I plug in t equals 0 into that equation, my x is 0. And my y is 0. When I plug in 1 in for t, my x is 2. I get negative 1 plus 7 is 6. If I put in 2, I get 4. I get negative 4, and 14 gives me 10. If I put in 3, I get 6. That'll be 8. If I put in 3, I get negative 9, and 21 is 12. Put in 4, I get negative 16, and 28 gives me 16, I think. Well, let's try that again. 4 squared is negative 16, with a negative in front of it. Negative 16 plus 28 gives me 12. 12 again. So then, I'm going to graph this, and I'm starting at 0, 0. I'm going to 2, 6. I know I'm going that direction. And then I'm going to 4, 10, 6, 7, 8, 9, 10. It's still going that way. And then I'm going to 6, 12. There, still going that way, and then one more. If I put in 4, I get 1, 2, 3, 4, 5, 6, 7, 8, 12, and it kind of just levels off there. It's kind of a going back down type thing. So that's graphing a parametric. Graph it, make sure you put the arrows in to see which directions they are going. Polar coordinates and equations. We have some substitutions. We know that r squared is equal to x squared plus y squared. We know that the tangent of theta is equal to y over x. We know that that's true because of those, that x is equal to r cosine and y is r sine. So what can we do with that? Well, you'll do plenty of simplifying with that stuff. I'll just leave that there. I don't think I have an example for that. I want to find the distance between these two points in polar form. So what I'm going to do is I'm going to say D2 is equal to my radius 1. I'm going to go with this being my radius 1, so I'm going to go 4 squared plus 6 squared minus 2 times 4 times 6 cosine of 135 minus 30. Simplifying that down, I get 16 and 36 minus 48 cosine of 105. And let me get my calculator out. Looks like 52 minus 48 cosine of 105 equals 64.4 blah 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 blah. And square root that, I get that the distance between those is 8. So, distance between those 2 points. Alright, graphing curves in polar coordinates. Solving linear and non-linear. We did plenty of those, I thought. I don't know. Come with questions. Gaussian elimination, augmented matrix. We did plenty of that. matrix operations know how to 1, 0, 1, 0, 0, 0, 1. That's the identity matrix. Know how to multiply. Know how to do row operations to get something in that form. So we would be solving 1, 2, 3, something like that. So this is an easy way. If you have 3 equations, 3 unknowns, these are the x, y. Excuse me. Then there's the number. And so that would mean that x is equal to 1, and y is equal to 2, and z is equal to 3. Multiplying 2 matrices. Let's say I have 1, 2, 3. Oh, I think I actually have an example here. Yep, I knew I did. If I wanted to multiply 2, or A times B, we know this is 2 rows and 3 columns. We know this is 3 rows and 2 columns. For us to be able to multiply them, the middle 2 have to be the same, and our result is going to be the outside numbers. So I know that my result is going to be a 2 by 2 matrix. So I'm going to take 1, 2, 3 times 1, 0, 2, and so it would be 1 times 1 plus 2 times 0 plus 3 times 2, and that's going to all go in that first position. And that looks to me like I get 7. And then I'm going to take the first row times the second column to get first row, second column, which gives me 7 also. And then to get the bottom row, I'm going to take the bottom row times the first column, which gives me 4 plus 12 is 16, and 18 minus 5 is 13. So multiplying matrices, got to know how to do that. Know how to find inverses. If I have a matrix, say 1, 2, 3, 4, and I want to find the inverse of it, I just put it so the first matrix, and then this will be the inverse over there. Using to solve a system, yeah, that's what we do it for. Oh, the determinant. So if I have determinant A, B, C, D, my determinant would be 1 over AD minus BC. Well, no, that's not the determinant. AD minus BC is the determinant, and we use a formula to get inverses using the determinant. All right. Minors and co. So if I have, and I want to find the determinant of a 3 by 3, let's say I have 1, 2, 3, 1, negative 2, 1, 4, negative 3, negative 2. And I want to do the determinant of that. So I am going to expand about the first row. And so I'm going to have 1 times, and then I'm going to have the determinant of the small matrix. If I cross out the 1's row and the 1 column, I'm left with negative 2, 1, negative 3, negative 2. Now remember, it goes plus, minus, plus, minus, plus, minus, plus, minus, plus. So I have to have a minus 2 here, and then 1, 1, 8, negative 2, plus 3 times the quantity 1, negative 2, 3. And that's how I would find the determinant using a cofactor expansion, using the minor. And so then I would say, just to continue, I guess, I would go 4, negative 2 times negative 2, minus negative 3, minus 2 times the quantity of